Hi all, it's Mr. Yeager. This is one extra video to help out with the relationship problems involving projectile motion formulas for AP Physics. Again, this is the more common use of what they're going to be asking for with the problems in this case of what would this equal, how can I find, what would the velocity be. So this would be relationship, but also some equation stuff that we're going to play with too, because a lot of times you'll get questions that'll say, what is time in terms of delta y and blah, 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 blah. Okay? So a couple things I just want to show real quickly. I'll start off with some equation manipulation. Okay, if we have this equation, delta y equals v naught yt plus 1/2 gt squared. Okay, really quick, for zero launch problems, zero launch, okay, where v naught y is equal to 0, and we have delta y, we have and we have g, but we know v naught y is 0. They might say, what does time equal? All right, and hopefully you guys can see this. All they would do is you do delta y equals 1/2 gt squared. All right, because v naught y is equal to 0, that gets canceled out. And then we basically just rearrange to solve for t. So I multiply 2 over, okay? So 2 delta y equals gt squared. Divide by g, 2 delta y over g equals t squared. And then if I want to really get specific, t would equal the square root of 2 delta y over g. So technically that is the formula you're using when you solve for time. Obviously if you have the numbers, I would also just plug everything in and solve from there. But that would be what time is equal to for a 0-degree launch. Now what about for an angled launch? Okay, for an angled launch, one where you're launching it upwards. Okay, we're not going to look at it going downwards. As we saw in the other video, you get the quadratic equation. We have delta y equals v naught yt plus 1/2 gt squared. Again, I'm trying to solve for time in air. What would time in air equal if I shoot it and it ends and lands in the same spot? Okay. Well, we then know delta y is equal to 0. Delta y is equal to 0. Okay. And so what I have here is I have 0 equals v naught yt plus 1/2 gt squared. All right. If I try to solve for this, again, technically, and not technically, for real, okay, the negative, this is going to be minus 1/2 gt squared because g will be negative while v naught y should be positive. So if I rearrange this, I send 1/2 gt squared to the other side, equals v naught yt. And again, I'm trying to solve for t. What am I going to do? I'm going to multiply the 2 over, so I get gt squared equals 2v naught yt. I'm going to divide both sides by gt. I'm just going to go ahead and do it right away. Divide both sides by gt. Okay? Because that'll eliminate one of the t's on this side, eliminates that g, so I'm left with t, eliminates the t on the other side. So the time in air for an angled launch is 2v naught y over g. That would be your answer. Okay? So that would be the time in air for an angled launch. Okay? Is what we're looking at there. All right. So those are kind of a couple things I just wanted to show. Be prepared. I'm not finished yet, but be prepared where they'll go, what does v naught y equal? Okay, in terms of v and theta. Again, it's v sine theta for angled launches. Vx would equal v cosine theta. So coming back to this problem, they could always make you say this is equal to 2v sine theta over g. That would be perfectly correct because that's what v naught y is equal to. Again, the problems are very specific, saying you must use v, theta, and any fundamental constants, which would mainly be g, to solve these problems. So you just got to be ready to manipulate the equations appropriately. So the last thing I wanted to kind of share would be some relationship problems. Delta y equals v naught yt plus 1/2 gt squared. Okay, so I'm only going to show a couple. There's other ones you're going to have to obviously discover on your own some. All right, what if I'm doing a zero launch problem? A zero launch problem again. That would mean this goes away. I'm left with delta y equals 1/2 gt squared. And I did this once before. What if I wanted to say, how much would I have to increase my height? All right, what would I have to increase my height by to double the time that the object's in the air? All right, how much would I have to increase my my height by in order to double the time that the object is in the air? So other words, we're saying I have one object that goes off from delta y and ends with time t. What do I need to increase my height to? Whoop, ah. What would I have to increase my time to? Or sorry, my height, I keep saying time. If I want this thing to now stay in the air for 2 times the time of the first time around. Well, this is our classic, again, relationship problem. This is how we handle all of these. All right, I have my equation up top or right here in the middle. Get rid of anything that's a constant. What's a constant? The 1/2 and the g, so I ignore that. So I see I have a relationship of delta y is related to t squared. But again, remember, I squared the time. So what does that tell me to do? And again, there's no coefficients in front of them now, so whatever I add on this side of the equation, I need to add to the left side. So I put 2 right there. The thing is, what's that 2 going to do? It's going to get squared. So delta y is related to 4t squared. What did I add? I added the 4 now. I'm going to have to go 4 times the height. I have to quadruple the height to double the time in the air because of the relationship between delta y and t. Now, the thing is, how would this affect my range? Well, delta x equals vxt. I said I didn't do anything to the speed, okay? But I did increase the time by 2. So actually the height won't do anything. The height does not affect my horizontal velocity, my horizontal range, okay? No, it does. Sorry, what am I saying? The height does because obviously it'll increase the time in the air. Well, if I double my time in the air, it's delta x is related to t. This is the easiest one. If I double time, I double my range. Okay. I mean, a lot of this stuff you just got to practice with. You got to move through. I mean, what if I shoot something off at v and then I shoot another object off at 2v? How would this affect time and displacement? This will be the last one I do. How would this affect time and the range that it goes? All right. Actually, let's add in how will that affect the height that it goes to? So basically, there are 3 main points. All right. So what do? Well, if I double my velocity, what does that do to the sides of my triangle? This one should not be that difficult. Okay. I have Vx and Vy up here. What would happen to Vx and Vy? Well, if the formulas for Vx is V cosine theta and Vy is V sine theta, the angle doesn't change, so I can ignore that. So if I double the velocity, I double the component velocities. So I have 2Vx and 2Vy. Okay, I've doubled the y velocity. All right. I'm trying to solve for time in air. So time in air. So that's again delta y equals v naught yt plus 1/2 gt squared. Okay. What we figured out here is again time in air. I'm going to set delta y equal to 0. So I'm left with v naught yt plus 1/2 gt squared. Again, technically this will become negative, so I'm going to move that to the other side and just keep the positive sign. Let's remove everything let's remove all the constants. 1/2 g goes away, so t squared is related to v naught yt. I can eliminate one of the t's. So t is directly related to v naught y. So what is this telling you? If I double my vertical velocity, I'll double the time that the object's in the air for. So boom, the answer is it'll double the time in air. So there's my first answer. If I double my velocity, it'll double the time. What about my range? Well, delta x equals vxt. Now I see people make a common mistake here. They go, oh, I just learned it doubles the time, so that'll double the range. Wait a minute, what else did we also do? We also doubled vx. So 2 times 2 is 4 times the range. All right, if it's in the air for 2 times the amount of time, I'm actually able to quadruple the range because my velocity also doubles. So I'm going to have 4 times the range. What about delta y max? Now this is why I introduced that second formula. I wouldn't deal with time here. I'd go to this formula, not that delta. Vfy squared equals v naught y squared plus 2a delta y. This is 2g delta y. All right. The thing is, if I'm looking for the maximum height, up at the very top, final y is 0, so this goes away. So I'm left with V naught y squared is related to 2g delta y. Okay? And again, I'm ignoring all the positive and negative sign because, again, technically this would be minus because g is negative. Okay, I'll just put it that way. So I get rid of any constants. 2g is removed. So v naught y squared is related to delta y. What had happened to my v naught y? It got doubled, which then gets squared. So what does that mean? 4 v naught y will, squared is related to 4 times the height that it goes as well. So you can see, if I double the velocity that it is launched, I will double the time that's in air, but it will quadruple both the maximum range that it goes and the maximum height that it is released, that it reaches. All right. So you're going to have to probably be prepared for other ones. I'm not going to show everything here, but I mean, you get I basically have shown the whole process of any problem that could possibly come up with this. So be prepared to, or variations, I should say. I probably have not hit everything, but I feel like you have enough information that you can obviously analyze and interpret any other problem that's not specifically done on the board right here now. All right. So thank you.